Hello everybody and welcome to today's lecture on vector math. This is going to be a very exciting presentation about useful maths that you're going to be able to use when you are developing your gameplay prototype within Unity. Video games are a simulation of space. All that maths that you did in high school and maybe wondered, when am I ever actually going to use this in real life? The answer is the creation of video games. Because no matter what the game is and how realistic or unrealistic it may be, you are still attempting to somewhat simulate the motion of objects within space. They are made up of objects, which are things, interactions, the way these objects interact with each other, and behaviors, the rules that define how these objects can interact. And this is all happening within a space. Whether this is 2 dimensions, 3 dimensions, or any other spatial dimensions, we need a way to describe the space so that we can discuss the placement, rotation, and motion of things within the space itself. Before we go any further, let's set out some definitions for what we are actually talking about when we discuss directions and space itself. In games and most problems we come across in life, we are working in Euclidean space. If we're working in non-Euclidean space, then something has gone wrong. Generally, what this means is that everything is as you expect it to be. If we're working within 2 dimensions, we have a left, right, and an up, down. If we're in 3 dimensions, we have a left, right, up, down, and a forward and back. So width, height, and depth. When discussing Euclidean space in 3 dimensions, as we have in real life, we can relate to the directions of up, down, left, right, and forward and back. For games, though, we want to discuss things in absolute terms. In real life, when something is in front of you or behind you or to the left or right, this is usually done relatively to your frame of reference and where you're standing. We can do this in video games, and you may have seen this already with parent and child relations in Unity. But what we really need is an absolute way to determine where something is within space. The usual practice to do this is to label our axes with an X, Y, or Z. Unfortunately, it's not quite that simple because not everybody agrees on how we should be labeling the spatial axes. In Unity, the Y-axis is up, with negative Y being down, the X-axis is right to left, and the Z-axis is forward to back. In the Unreal Engine, which some of you may have also used, you'll know that Z is up, Y is to the right, and X is forward. In Maya, Y is up, X is right, but Z is backwards, so it's actually been flipped there. For the rest of this lecture, and pretty much any time I'm discussing directions, my frame of reference is going to be the way that Unity describes it. So X goes from left to right, negative to positive, from down to up, and from back to forward. Let's talk about space. Our next step is to think about how we can represent movement, rotation, directions, scaling, any operation that we might want to do within a spatial frame of reference, how we can represent that within a space. Our main solution for this is to use vectors. A Euclidean vector, but from here on we're just going to be referring to it as a vector, is a geometric concept which we use to represent the properties of something within a vector space. This could be used for a position, a direction, a rotation, a velocity, an acceleration, and many other things on top. A 2-dimensional vector is simply a vector in 2 dimensions. This means it only has an X and a Y component. There is no forward, back, or depth component to a 2-dimensional vector. This is most often used for 2-dimensional games, so this could be side-scrolling platformers, it could be top-down shoot-'em-ups, and even in 3D games, we still use it for game UI. In code, so when you are developing this in Unity, it's pretty simple to access this. There is a class called vector2, which represents a 2-dimensional vector, and you'll be able to see that it has two components in it, an x and a y value. We can represent two-dimensional vectors by using some brackets and putting some numbers in. So our examples here, we have 0.2 on the x and 0.13 in the y, 13 in the x, 37 in the y, and 0 in the x and 1 in the y. These are just some sample examples of what a two-dimensional vector can look like. When we add another dimension, all we need to do is add another number. So the call for this in Unity is vector 3 rather than vector 2, and this just means that it has 3 components instead of the 2. And again, the examples for this, writing this down, are pretty much what you expect from vector 2, just with another number added onto it. The word for vector comes from the Latin for carrier, and this is because it actually tells us what a vector does. It carries something from one point to another. Even when we discuss the position of something in space, that's not a point. What it is it's a vector that represents what magnitude of movement and direction would need to happen to move us from our origin of our frame of reference to the current position that we want to have. Within that is a clue to what makes up a vector. Generally, they have two properties: a direction, which way is the vector pointing, and a magnitude, how long is that vector. So from A to B here, normally when we write out a vector, it's the start point, end point with a little line above it. So this vector AB carries the point from A to B. The direction of this vector is a short line pointing from A to B, and the magnitude is the length of the line that we need to take us from A to B. So the direction of a vector defines which way in space a vector is pointing. For example, up is 0, 1, 0 because we're moving up on the y-axis. And our direction is usually a unit vector. This means it has a length or a magnitude of 1. So some examples here. A 2D vector pointing up at a 45-degree angle has an x and y value of about 0.7. A two-dimensional vector pointing to the right is 1, 0. And a 3D vector pointing away to the upper right would have these values here. So this is 3 dimensions. We're kind of limited in how we can display this on a 2D PowerPoint slide, but you'll have to use your imagination. If you were to calculate the magnitude of each of the vectors here, they would be 1. They are unit vectors. They don't have a length beyond 1. They are just used to represent a direction. The magnitude of a vector, on the other hand, defines the length of a vector, or how big it is. So magnitude, we get this from taking the square root of each component squared individually and then add them together. Or we take x squared plus y squared and then find the square root of that. Or we add in the depth when we want to do this in 3 dimensions. So some examples again. For up, it has a unit length of 1, because if we do 0 squared plus 1 squared plus 0 squared and square root all of that, we get 1. Magnitude is a scalar value. So a scalar value has no direction. It is just a single number. So another example here, if we have a two-dimensional vector of 3 in the x-axis and 5 in the y-axis, to find the magnitude or the length of this, we square the components individually, and then we find the square root of the entire thing. So this means that this vector has a length of 5.568. If we do the same for this one, we get a length of just over 6. And in 3 dimensions, we do the same thing, just with 3 values instead. It scales very nicely. On to talking about normalizing vectors. When we normalize a vector, this is the act of taking a vector of any length, so any of the ones we've used so far, and we reduce it to just represent its direction. So it's now a length of 1, it is a unit vector. Again, a unit vector is a length that has the same direction as the original vector. It is 1. So we normalize a vector by dividing each component by the total magnitude. So it's a 2-step process. So if we have a vector here, a 2D vector of 3, 5, we work out its magnitude to be 5.568, which we had on a previous slide. So this is our magnitude or length. If we continue to find the unit vector for this, we divide each component by this magnitude, which is 3 divided by 5.568, and then 5 divided by 5.68. So this gives us our new final unit vector of 0.54 and 0.898. This right here is our new normalized vector. It has a magnitude of 1 and it simply represents the direction of an initial vector. And we'll discuss some uses of this later on. The really handy thing about vectors is that we can combine them together in really useful ways. If we have 2, 3, 4, any number of vectors, we can add them together and this will create a final motion vector. This is really good when you have inputs from different directions or different sources and you need to work out what the overall force is. For vector addition, all we do is we add the individual components together. So if we want to add 0, 4 and 2, 2, this simply gives us 2, 6 because we add 0 plus 2 and 4 plus 2, which gives us 2 and 6. And once again, the exact same goes for 3 dimensions. We just add on another component and treat it the exact same way. So to work through an example, if we have a vector of 0, 4 pointing up the way, and we want to add on a 45-degree angle 2, 2 vector, we get this by pretty much sticking them end to end, and that gives us the new result, which is 2, 6. Same again, even if we have negative numbers there, we add them together, it's the same as sticking them end to end, and our final result is the summation of all of the input vectors. One of the most frequent things you're going to be using vectors for is to represent the position of objects within your mechanic prototype. So vectors are commonly used to represent positions within 2D or 3D space. Again, the positions here aren't really points in space, it's us saying that this object is X amount of distance and a direction from the center of the frame of reference. If it doesn't have a parent, this is the center of the world, 0, 0, 0 within Unity. If it is the child of another object, then its position is relative to that object's position. And you'll see this in Unity at the top of your inspector in the transform component. You'll see an X, Y, and Z. Vectors can also be used to represent rotations around an axis. So to make an object spin, we could increase its yaw or Y rotation. So the Y rotation is the rotation around the Y axis. Imagine it as a pole going through your object that it is rotating around. So X is the pitch, which makes it look up and down. Y is the yaw, and Z is the roll, which makes it roll about itself. As a vector, we have pitch, yaw, and roll. And once again, you'll see this in the inspector on the right there, X, Y, and Z components for Euclidean rotation. There is another form of rotation, which we're probably not going to go into, called quaternions, which helps avoid some problems that you might get if you're doing very complex rotation, but for now, just imagine it is X, Y, and Z rotations. Vectors also are used for the scale of an object. This is just a number that says, how should this object be scaled along its X, Y, and Z? And again, you'll see this in the inspector at the transform component. Scale is a multiplier, so our default scale is 1, 1, 1. Normals. Not to be confused with the normalization that we discussed earlier. If you've done much computer arts, then you're probably familiar with the concept of normals and how if they are incorrect, your object is going to look weird when it gets shaded. A normal, or a surface normal, is the direction that tells us which way something is facing. If we have a flat plane, the normal is facing up. You can see on the right here, this yellow plane is kind of lying on a ground, and the front normal is up and the back normal is pointing the other way. Below it, we have a more complex mesh, and you can see that the normal is always pointing perpendicular to the surface that it's on. Normally, normals are just used for calculating lighting information, but there are some other uses which we'll be able to see. So far, this has been a lot of maths, and I'm sure a lot of you didn't come here to learn this stuff, but it's an important part of how games are put together. Even if you are not developing games or engineering them rather, working within engines, you're going to have some sort of idea of the 3D space and how objects move relative to each other. So this might find ways to work into the work that you're actually doing. Even just being able to talk about it is going to help you in any future career. Luckily, to make things easier and to skip some of the stuff that we've talked about so far, Unity, Unreal, and pretty much any modern game engine or framework have helper functions to help do a lot of this stuff for you. So let's look at some of those tricks that we can use in Unity to make things a little bit easier. I've touched on this earlier. In Unity, we have a vector2 and a vector3 class, which are used to represent two-dimensional and three-dimensional vectors. Just like any other variable, like float or int, or your own custom classes, you can create a vector2 and vector3. You probably already use them somehow when moving objects around, and a lot of this stuff should hopefully be a little bit familiar to you. So in code, it's going to look like this. To make a two-dimensional vector, we say vector2, we give it a name, and we say that this equals a new vector2. Vector3, once again, it's the exact same, but we changed the name and we add in another value. The F here means it's a floating type numerical. The new here means that we are making a new instance of this class and to store it in a place called my3dVector. The two vector classes have a bunch of handy helper functions built in. Assume that you have a 3D vector called velocity, which is used to represent how fast something is going and which direction it is going in. You could call your velocity.normalize, and this is going to take that velocity 3D vector and return to you a unit vector instead. This way, you now know which direction you are moving without needing to worry about the magnitude. Or you could do the following. You could say vector3 direction equals velocity.normalize, which instead of changing the velocity vector to become normalized, losing the original value, we're now copying it into a new value called direction. If you want to know how fast you're going, but you don't care about which way, this is usually used if you want to change animations based on the speed that something is moving, or if you want to activate something if you're going too fast or too slow. We just need to get the magnitude of our velocity vector. It cares not about which direction you're going, it is just going to return a number that represents the speed. So to store this, we can just say float current speed equals our velocity vector dot magnitude. If for whatever reason you might need to access and modify individual vector components, you can do that as well. If you have a 3D moving character and you want to stop them from falling, you can just jump into the velocity value and set the y value to 0. So now any y speed that it had is removed and it's going to stop falling. And there are loads more functions that you can use. Make sure you check the documentation on the Unity website or whatever engine you happen to be using and see what is expected as an input, what you should get as an output, and also what the processes are. A few examples here. Distance, you provide two vectors that represent points in space, and it is going to tell you the distance between them. So if we have a line here, it's going to return this if that's between two different points. Reflect will take a surface and a normal, and we provide an input vector, and it is going to reflect that off the surface as if it's like a mirror. An angle, we put in two vectors, and it is going to tell us the angle between them in degrees. A couple of advanced techniques which you may find useful in your prototype. The dot product, or the scalar product, is a mathematical function that takes two sequences of numbers, vectors are sequences of numbers, and reduces them into a single scalar value, so one number. So we can take two vectors and we can, for all intents and purposes, multiply them together and get a single value out of it. If you're wondering why we would want to do that, the dot product tells us how much of one vector is pointing in the same direction as another vector. So if we have two vectors called A and B, if A and B have the exact same direction, then the dot product is going to be 1. If A and B have the opposite direction, the dot product is going to be -1. And if they are pointing at right angles, so they're not pointing towards or away from each other, the dot product is going to be 0. So it's entirely based on how much of the same direction they share. You may be wondering why we want to do this. It's really good for quickly comparing the directions of two vectors. So now we can tell if our player is touching the ground. We look at the normal of the collision with the up vector, and if they match, so if the dot product is more than 0, then we know that the player has landed on an object. And that means the player is probably touching the ground. In reality, if you want some complex collision detection, or if you have a lot of slopes, or if the player can change gravity, this won't work as is, but the same basic concept applies. In Unity, it's incredibly simple to use. All you need to do is call vector3 ... and pass in two vectors, and it will give you a floating point result. The cross product, on the other hand, is a little bit more complex conceptually and how we might use it. It is the other way to multiply, and that's in quotes because it's not really multiplying two vectors together in a three-dimensional space. You can do it in 2 dimensions, but it's not really the same thing. So when a dot product gave us a single scalar value, the cross product is going to give us a completely new and different vector value. If we put in 2 vectors into the cross product, the result that it spits out is perpendicular to both of the input vectors. So this diagram on the right here, if I grab a pen, we have vector A, which is our first input, which is pointing along this way, and we have vector B, which is pointing along this way. When we do the cross product, the result that we're going to get is either AB, which you can see is at right angles to A and B, or if we do it the other way around, we are going to get down the way. So with cross product, the order of the inputs actually matters and will give us a totally different result based on which way we put them in. We can use this to give us the surface normal of any plane. Probably not super useful in your day-to-day, but there are specific use cases where a cross product can be handy. Here's a little diagram of how this actually works and what the output changes based on the inputs that you're giving it. So as this rotates, it's going to change what we're getting out of it. So that's a lot of maths for a program which isn't really supposed to focus on it, but it will come in handy for the development that you're doing. You don't need to know all the proofs and the reasons for why all this stuff is the way it is. If you're curious, you can go get a math book at the library or come speak to me in class. Knowing how to navigate the 2-dimensional and 3-dimensional spaces is really important, however. It's important for developing your prototype, but also for communication between you and other team members in future development. Vectors are the building blocks of space within game engines. So hopefully this lecture has given you some of the language that you need when you're trying to find solutions to issues you might run into. You might have a better idea about what to be searching for when you're trying to solve a very specific problem. And now I can also point you back here during some of our live practicals and in class when there might be questions about how you can solve specific problems. That's all for today. If you have any questions, please come find me in class or send me an email. And I hope that was helpful. I'll see you all next time.